Good.
Okay. Hi, I'm Crystal Butler from New York University. I'm going to talk about MiFace, a framework I and my co-authors developed for defining facial communication mappings using a 3D avatar and crowdsourced natural language labels. I'm going to give a little bit more information about the context of this research and the motivation behind it, because I find we get a lot of questions about that. So I will get to the actual research a little bit later, but there's some information first. First, let's clarify what a facial communication mapping actually is. Facial expressions are one modality of nonverbal communication, and like words, they have both a semantic component and a syntactic or structural component. The semantics are meaningful information conveyed to a viewer, the perceiver of the signal. The syntax comprises the dynamics of craniofacial muscle activations, which would be, for example, oops, oh, that's not what I meant to do, hang on. So, like this, or this, those are muscle movements. The image shows expression semantics reduced to a single natural language label, which is here, a key part of the MiFace framework that I'll go into shortly. Some of you may be familiar with FACS, the gold standard of facial movement encoding, which provides the basis for modeling muscle activations in our framework. FACS defines numbered action units, or AUs, for each individual muscle involved in producing facial expressions. AUs can be further described using a discrete intensity scale ranging from A to E, which we transform to a continuous weighting ranging from 0 to 1. FACS is not meant to be a guide to interpreting expressions, only a tool for systematically describing facial behavior. However, the FACS Investigator's Guide contains an emotion prediction table which lists 6 basic expressions of emotion and associated sets of prototypical AU activations. 40 years after the initial publication of FACS, those same 6 basics, and some people include contempt as a 7th, are the only generally accepted facial expression mappings. Here we have images from the Cone-Canade CK plus facial image expression database, alongside example MiFace expressions, here. Displaying disgust, sadness, fear, surprise, happiness, and anger, which are the 6 basics. The CK Plus database is an example of labeled training data that can be used in machine learning for automated facial expression recognition. CK Plus and similar image sets are FE mappings of AUs to appearances and emotion labels, typically constructed by taking hundreds of posed photographs displayed by human FACS experts or actors who have been coached by them, which is an expensive and time-consuming process. The requirement to create enough labeled images to provide a variety per expression required for machine learning limits the number of expressions that can be modeled in this way. Even the smaller expression sets required for social sciences studies are constrained by the availability of human and technical resources. In both fields, emotion labels for images are usually validated by naive human judges under a forced choice experimental design in which they select from a predetermined list of labels, generally determined a priori by experimenters as the emotions being displayed. So for example, I might show you this image and ask you whether it displays fear, anger, happiness, disgust, sadness, or surprise. Those are your only choices. Facial expressions aren't just the concern of machine learning specialists who want to use facial feedback to sell us more soda pop, or psychologists researching emotion. They affect all of us. Around 65% of communication that occurs during human interaction is nonverbal. While we also use gestures, tone of voice, or posture to convey meaning, the face is our primary focus. Faces are so important that we have a specialized area of the brain for recognizing faces, the fusiform face area. And facial expressions can convey more than emotion. They can convey mental states such as interest or boredom, physical states such as pain, moods, social emblems such as politeness, information about individual identity. The current US president is a great example of that. And action tendency. My favorite example of an action tendency, which I believe is a major oversight that exists in facial expression mappings, is a combination of AU's 18, the lip pucker, and AU 22, which is lip funneler, and you put them together and you get the kiss. So humans send and receive facial expressions as social and emotional signals. Understanding the way humans recognize and display these signals can lead to improved diagnostics in medicine and psychology, as well as treatment tools in the case of conditions such as ASD or stroke. Shown here is a list of some conditions in which impaired facial expression production or recognition are correlated. With recent advances in machine learning, computers are able to perform tasks we once believed only humans to be capable of. Facial expression recognition is one example. Here are several companies who have production software that performs automated FER for tasks such as market research and usability studies. Two of the most well-known, Affectiva and FaceReader, can recognize individual AUs, but still only return metrics on 7 emotions, because there's no way to map the AU space onto a broader expression semantic space. As an aside, emotion, founded in part by Paul Ekman, who I showed earlier, was recently acquired by Apple. The flip side of recognition is expression production, which virtual humans are becoming increasingly adept at. Virtual humans can be found in characters such as in games, or as shown here, digital assistants. Amelia, here, is a digital IT agent. Molly is a nurse who lives in an app that can get feedback from patients to give to doctors. And at the bottom, we have an academic research project, which is a psychiatrist who can diagnose conditions such as alcoholism and major depressive disorder. Their facial expressions may be created by using techniques from animation, such as motion capture and retargeting, or by manipulating facts-informed character rigs, such as skeletons or morph targets. Morphs are digitally modeled target movements. Currently, the digital facial expression space is much larger than the recognition space, but the choice of how facial display semantics are represented is largely subjective. Creators are free to represent meaning with any facial displays they or their actors deem appropriate. All these avatars are displaying smiles, the most reliably recognized expression across cultures. Is Amelia exhibiting a confident smile? Is Molly exhibiting a polite smile? And is our psychiatrist showing an interested smile? Would those variations be appropriate in all contexts? We need to build facial expression lexicons that provide a ground truth of shared meaning so our digital counterparts can communicate clearly and understand the nuances of human behavior. So we propose the MiFace framework as a means to build such lexicons. MiFace uses a facts-based virtual human to display expressions and allows naive, crowdsourced judges to provide natural language labels for perceived signal values of those expressions. That makes MiFace reproducible across an infinite range of avatar appearances that can vary in age, race, and gender, for example. No facts experts are required to generate image sets or motion graphics, and developers are free to express the entire range of movements the human face is capable of in any combination in a way that is consistent across facial morphologies. So, to prototype the framework, we first needed to build a facts-based avatar and computationally generate facial expressions. After testing several alternatives, we decided to use FaceShift, also since acquired by Apple, as the primary tool for avatar creation. FaceShift provides a basic polygonal mesh and repertoire of face movements, or morphs, informed by facts. By acquiring a depth map of a target actor using a Connect sensor, the base mesh was transformed to the target's geometry. In addition, phase shift allows for modeling custom morphs. The generated mesh and customized morphs were exported to Maya for hand modeling adjustments and to design any missing morphs. Morph activations were weighted on a scale from 0 to 1. And finally, the avatar prototype was skinned with a low resolution texture. The resulting avatar was capable of 28 fax movements. So with the potentially infinite number of movement combinations and intensities available, we decided to run 2 proof-of-concept observer judgment studies with a constrained set of AUs and weights. The studies used crowdsourced naive judges to decide whether expressions were believable, and if so, to label them. 22 key AUs were selected by combining the guidelines for identifying basic expressions of emotions as outlined in the Facts Investigator's Guide, and combined with criterion coding of expressions from the Facts certification test. Weights were fixed at levels at which they were clearly discernible. All combinations of 3 and 2 AUs were computationally generated based on the selections I just showed, and used respectively in 2 proof-of-concept expression labeling studies. This grid shows a small sample of triples, or combinations of 3. Some generated images had to be removed prior to testing because additive effects of particular AUs at these weights were resulted in impossible configurations. So, next step, human judgment studies. We crowdsourced participants from Amazon's Mechanical Turk. Images were sent for phase 1 testing in 2x3 grids for binary classification by 3 Mechanical Turk workers each. Workers checked a box to indicate yes if they believed the expression could be displayed naturally by a human. If 2 or 3 raters said yes, the expression went on to phase 2 for labeling. This figure shows an example image grid. So for study 1, phase 1, which used 3 action units, we began with 1,380 images, and 341 ended up being selected as recognizable. Study 2, phase 1, we used 2 AUs. Out of 229 candidate images, 114 passed on to the second phase for labeling. In phase 2, 40 Mechanical Turk workers each provided the single word label they felt best described a facial expression. This figure shows the instructions given to participants, showing an expressive face here, to be labeled, along with a neutral expression, which is an expression-free face, and that was provided as comparison. Each target image was shown in this format. The next step in our process was finding a way to reduce a set of free response labels to a single representative label. This was absolutely the most challenging part of our project. We could find no standardized quantitative measure of word-word synonymy, which is what we required to analyze our label sets. We tried several algorithms that use the Princeton WordNet ontology, but none provided consistent results. We then tested 2 natural language processing algorithms, Word2Vec and GloVe. GloVe performed better over our input domain. To calculate similarity scores, every label is paired from all others within a set for n times n minus 1 over 2 pairs. In the case of 40 labels, that gives us 720 set. A cosine similarity score from -1 to 1 was assigned using pre-trained GloVe word vectors with -1 indicating opposites and 1 an exact match. The scores were summed, and the top scoring word became the expression label candidate. Before deciding the top scoring candidate label was our set representative, we wanted to test overall semantic coherence of the set. In other words, we wanted to ensure that the label represented a single cluster of strongly related words. We decided hierarchical agglomerative clustering was best for our analysis because it generates an arbitrary number of clusters based on distance measures, our cosine similarity scores. As shown in this figure, a dendrogram. Clustering starts with individual words at the leaf level, so down here, and joins them as you move up based on how closely related they are. All clusters eventually join here at the top, So in order to get a meaningful clustering result, you need to provide a cutoff. Expert testing on a sample of label sets determined that a cutoff of 0.8375, which is here, combined with a requirement of greater than 75% set membership in the primary cluster gives a good indication of coherence. So in that case, what we have here is this is our primary cluster right here, and these get cut out. So in study 1, our 3AU study, phase 2, 157 of 341 label sets passed clustering, and study 2, the 2AU study in phase 2, 63 of 114 sets passed. So after beginning with 1,609 candidate images, we finally got 220 expressions reliably mapped. A few examples are shown here with their associated AU weightings. We've got embarrassed, curious, and hopeful. To the right is a table of 51 unique labels that were returned across both studies. As you can infer from the ratio of expressions to unique labels, image label mappings are not necessarily one-to-one. There's plenty of future work to be done in our framework, such as improving avatar quality and word synonymy scoring. Nonetheless, we expanded the expression mapping space by about a factor of 8 with these 2 proof of concept studies alone. User interfaces that can understand and model social and emotional behavior are critical to advancing the supporting role technology plays in our lives. We believe MiFace can be used to develop a common ground of facial expression production and recognition that we hope will lead to improvements in areas such as game character design, the development of intelligent agents, machine learning, and psychological testing and treatment. So thank you very much for your attention, and I'll take any questions.
So I have a question. So you used a particular piece of software, which sadly is no longer available to regular folks to use, to create the faces. What difference do you think there would have been, if any, if you had used one of the other pieces of software to actually create the avatar expressions?
The goal is to get the most realistic movements possible with a secondary goal of a realistic appearance, although that is not necessarily required. You don't need to have hyperrealism for people to interpret expressions. So if there was something out there that we could have gotten better movement modeling results or better morph targets out of, that would have been great. I can't say that this prototype is actually perfect in that sense. That's something we're still working on.
Okay.
Does that answer your question?
Yeah. Anyone else? Don't make me be the only person asking questions. Come on, this is your chance to actually talk with and ask questions of the speaker. You won't be able to ask questions of the ACM digital library as easily. No one else wants to take me up on this?